So this should all be review. It's the definition of the stationary distribution of a Markov chain. You should know it from 160A, but I'm going to give you kind of a shorthand definition, something that you just kind of have to know, and that's it. It's a major sort of point in the class. And so the way you start is first, you can't define any stationary distribution before you have a Markov chain, and you don't have a Markov chain before you have one-step transition probabilities. So we're going to start out with one-step transition probabilities, right? These PXYs. And as we saw in the previous segment, these are just numbers that sum to 1 with respect to the second coordinate and are non-negative, right? So they're probabilities of transitioning, that a chain transitions from the state X to state Y in one time step. And so once you have this, right, imagine as soon as you have these numbers, right away underneath there's going to be this Markov chain X that you've just created out of thin air, and that Markov chain is going to have some probabilistic behavior, right? It's going to move in accordance with these numbers, right? Whatever you put in there, right, under the small set of conditions on the PXYs, non-negative and summing to 1 with respect to the second coordinate. So now let's move over to pi. Once you have the PXYs, the transitions, any function pi from the state space S, which is the same state space that X takes values in, right? So X, the Markov chain, takes values in the state space, and that's the same S that's right there. This is a function from the state space to the interval 0 to 1. It's called the stationary distribution once it satisfies 3 properties, and the first one you should know, you should kind of recognize right away. Each pi x is non-negative. Essentially, that's the same definition as right here. They sum up to 1. So both of these, for example, imply that pi x is less than or equal to 1, which explains why the numbers here in this range go from 0 to 1. And the more important condition is this condition 3, which can take one of 2 forms, either 3a or 3b. So you need to verify only one of these, right? No need to work on both, and in fact one of them implies the other, and we'll come back to it. As soon as you verify one of them, you know that pi is going to be a stationary distribution, right? So in fact this condition may kind of be dropped. So now that I'm thinking about it, this is a little bit suspect because I already defined the range to be in 0 to 1, right? So essentially you could maybe drop that first condition and just make sure, you know, this is a distribution, right? Stationary distribution is the key word, and so the probabilities, these probabilities better sum to 1. They better be between 0 and 1. So here and here, and however you want to, you can either specify, the fact that they're between 0 and 1, or you can say that these two imply that they're bounded above by 1, however you want to do it. But the more important condition is this one in 3. As soon as you verify either one of these equations, and you'll notice this one is quite a bit simpler, you have a valid stationary distribution. So hopefully you're familiar kind of with this concept and have done it, maybe not in just the kind of the more abstract form that we're going to have to do it in this class with. A little bit of a kind of a side comment. Equation 3a, or condition 3a, is often referred to as global balance, whereas condition 3b is often called local balance. And we'll see that this is going to introduce the interesting theme of what are called reversible processes for us. So this is going to be a topic covered in homework 2. And we'll certainly come back to it. Reversibility is a really important concept in the natural sciences and physics and chemistry, and it's related, in fact, to entropy of processes and various properties of macroscopic and microscopic systems. And we'll come back to discuss some of these sort of more interesting details. So all these definitions are kind of motivated, by the sciences, but at this point, they're usually taught in a very abstract, mathematical way. So I guess the only other quick comment is that when you're verifying these conditions, you have to make sure to do it for, right here in this case, for each y, right? Pi y is equal to this sum for every y. And this local balance condition holds for every pair xy in the state space S. Okay, so maybe all this is a little bit too abstract for now, but you can come back to it, and in the next lecture we'll have a lot of examples where we're kind of just go through, the application of these concepts kind of to a number of different Markov chains, and hopefully you'll see a little bit better how it all plays out in application. In terms of kind of what I want you to take away, besides knowing these definitions, what you want to take away from this segment is what pi x really means, right? And this is kind of if you take anything out of this segment, this is really the takeaway. Pi x is the probability that our Markov chain x is in state x after a long time. This is a bit wishy-washy, right? It's not exactly precise, at least not yet, and we'll make it precise, and we'll explain why kind of this is. But an example of an application of this concept or of this definition would be the following one. The expected value of the Markov chain x at time k is about equal to this quantity, and the question is when, supply the answer. The answer is for k large. And so you can kind of think about what that means. On this right-hand side, what you're doing is evaluating the expected value of a random variable with distribution pi x, right? So everyone should know what this is, right? This is the probability that, some random variable takes the value x, and this is x itself, so this is the expectation of x, right? And I'm kind of matching these two together. I'm not exactly equating them. And the reason I'm not exactly equating them is because pi x is not the probability that x at time k is in state x, right? If it was, then this would be exactly true. It would be exactly equals. That's not what I'm saying. I'm saying that after a long time, meaning that for large k, pi x is the probability that xk is in state x. And so I could fill in a little bit to add a k here, right, is in state x after a long time k, right? So we're thinking that k is large, okay? And then at that point, this becomes sort of a good approximation, right? And you've already seen how to compute this quantity with first step transition analysis, and now you're seeing it, how to approximate it, with this stationary distribution, presuming that you can compute it. And this will be something that we'll devote quite a bit of time to. How do you compute these stationary distributions for any given Markov chain? And that means for any given one-step transition probabilities, right? It will come down to verifying these conditions, with local balance playing a fairly prominent role, and then global balance is sort of this more difficult to verify condition, but sometimes you kind of have to resort to it, right? The plan of action will be to start with this one, and if this fails, back up to here. Okay, hopefully this is not new, just maybe a slightly different rewording. And again, the main takeaway is, what is the stationary distribution? You should be able to give a clean mathematical definition like here, and you should be able to say what it means intuitively. It means that it assigns the probabilistic behavior to a Markov chain after a long time. And we'll try to justify that in the next segment. We'll try to understand why these definitions that are kind of pure mathematics correspond to this sort of more vague but yet intuitive notion.